behind me here, I have a series of functions that seem to have maxima and minima. You can see there's a maximum here, a minimum here, and this one has both a maximum and a minimum. So we're going to compute the derivative of these functions and evaluate them at the x-coordinate of these points to see kind of what that slope of the tangent line would look like. Because I have a sneaking suspicion that there's going to be a relationship between the derivative and these extreme values. Let's get to it. So in the first case, I have a function 9x to the negative 1 minus 27x to the negative 3. So if I compute its derivative, by the power rule, I get negative 9x to the negative 2 plus 81x to the negative 4. Now what I can do is I can factor out a 9x to the negative 2, which leaves me with this one is 9x to the negative 2 minus 1. So that's 9 over x squared times 9 over x squared minus 1. Which means if I plug in f prime at 3, that's 9 over 3 squared, which is 9, 9 over 3 squared, which is 9, minus 1, which gets me 0. So does that make sense? Well, I think so, because if we have the slope of the tangent line, you see that that slope is going upward until it gets here, where it planes off before going downward. So it goes up, 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 planes off, and then goes downward. So it hits 0. The slope of the tangent line is 0. Now continuing along, I have g of x equals the square root of x. Now there's an interesting trick about taking this thing's derivative, and that's the square root of x is also, this is a bad red marker. So the square root of x is also the square root of x squared. This is a very convenient way to represent this function because we know how to take that derivative. Now don't simplify this. If you simplify this, you'll end up with the wrong thing. We have to take its derivative first. So we take the derivative, it's 1/2 x squared to the negative 1/2. And then by the chain rule, we take the derivative of the inside, which is 2x. So those 2's cancel, and this is x over x squared to the 1/2. But as we saw before, x squared to the 1/2 is the absolute value of x. So the derivative of the absolute value is x divided by the absolute value of x. Now, if you go back and remember some of the previous derivatives we've done, we remember that the slope of the tangent line on this one is always negative 1, and over here it's always positive 1. So the left-hand limit and the right-hand limit are not going to agree. If I try to plug in 0 into this, no matter what I do, I'm going to end up getting something. If I plug in values that are slightly less than 0, I'm going to get negative 1. If I plug in values that are slightly more than 0, I'm going to get positive 1. They don't agree. Therefore, the derivative does not exist at 0. So in this case, the derivative was 0. In this case, it didn't exist. But an interesting thing happened. The slope of the tangent line was positive, and then it changed. This one was negative, and then it changed, even though it didn't go through 0. So keep that in mind. But over here, well, we know what h prime of x is. H prime of x is cosine of x. That's just one of our standard derivatives. And h prime at pi over 2 is 0, and h prime at 3 pi over 2 is 0. So that's interesting. At both the maximum and the minimum, the derivative was 0. Well, if you think about the slope of the tangent line, it goes up, up, up. It sort of planes off, down, 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 planes off, up, up, up. So what you're seeing is that when those slopes of the tangent line change directions, sometimes going through 0 and sometimes not, you're still having very special behavior. You're seeing the characteristic of the graph somehow be affected. So we say that points where f prime equals 0, or where f prime does not exist, are called critical points. And this is massively influential, as we're going to learn about how to understand the behavior of functions in their graphs.